Thank you. Yeah, thanks for inviting me. It's great to be back. I really enjoy the hackathons that I've been involved with the Encode Club. Yeah, I'm sure you're all going to have a great deal of fun. There's some great partners here. Yeah, I think it's going to be an excellent time. Really great time for everyone. Okay, a little bit about myself. As Anthony says, I run Extropy IO. We're based in Oxford. We develop blockchain solutions and also dabble with zero knowledge proofs, very interesting area. We love community education. We love giving workshops. Sadly, we can't do it as much at the moment as we'd like to, but so this is a great opportunity for us. If you'd like to get in touch with us, please do. There's some contact details there. I'm really happy to answer any questions you may have. Okay, so talking about blockchain, starting from the very basics. If you fall asleep this evening and forget everything else, a good starting point to remember is that the blockchain provides a trust layer without a central authority. Really, the fact that we don't have a central authority really is what you need to know about blockchain. Okay, so what makes a blockchain a blockchain? Well, this is what I think is particularly important. So our blockchains exist over the internet, and we have an overlay network on that, and we have a gossip network. So the idea with a gossip network is that the participants in our blockchain, they come together, and in a public blockchain, they don't have to ask any central authority to join or to leave. So because there's no central authority there. So it's an ad hoc network, and the reason it's called a gossip network is that they gossip around all of the information that they get. So all of the transactions that are received by the participants in our network are gossiped around to each other. And the nodes on the network, they join to any other nodes on the network. They will join to a few at a time, but they can join to other ones. So the idea is that if any nodes leave, that should be fine. The network as a whole can continue, and the information, all of the transactions within our network will get passed around to everybody in the network. So that's the first component I think is important. The second one, and perhaps the most important, is the idea of a shared public ledger. And I'm talking here about public blockchains. So you probably have come across the idea of a ledger in a bank before, the idea of some place where all of the transactions can be recorded. So in a blockchain, there is this idea of a ledger where every transaction that happens in the blockchain is recorded. And what makes a blockchain particularly special is the idea that this is shared and this is public. So it's shared in the sense that everybody has their own copy. Now, I use the word copy advisedly. It's not really a copy of anything else. There is no central one that is the master copy in any way. Everybody has their own, and they build up this copy of their own according to the transactions and according to consensus. So the updates to the ledger are done by consensus of the participants in the network. The third component is cryptography. I won't go into that in any detail, but it uses particularly public and private cryptography, something that was invented in the 70s and is the basis for secure transactions on the internet. And we use this in blockchain mainly in two ways. One is a way to prevent our transactions that are traveling across a potentially malicious network, such as the internet. It's to allow these transactions, to allow us to be sure that they haven't been interfered with. The second thing we use them for is in the form of identity. So when somebody sends a transaction, we want to have some information about who that person was. We want to be able to tie that to some form of identity. Now, you will probably know with networks like Bitcoin or Ethereum, there is a pseudo-anonymity. So your identity on one of those blockchains is an address, a wallet address perhaps, that is just a very large number. But it is important that we know for example, which wallet signed a transaction so that we know that it is the correct person spending some tokens in our network. So those are the two reasons, the two main reasons we have cryptography in our network. Okay, so what does that give us in terms of a blockchain system? Well, because we have a public network and this shared public ledger, there's a transparency, and the state of our ledger is verifiable by everyone. Everyone will know what the rules are in our network, and they can verify that these rules have been followed when we're updating this ledger, when we're updating the state in our system. And that state is updated based on consensus. And I will later on the consensus mechanisms that are used. Our blockchain also has resilience because in terms of the network, we know if one of the nodes is taken out of the network, somebody decides to leave, that will not affect the network as a whole. Other connections can be made between the participants, and the transactions will still flow around the network. The whole network will proceed. And thanks to that, there is a censorship resistance. So if a particular government decides it doesn't like what the network is doing, what our particular blockchain is doing, there's very little that they can do about it unless they effectively block all of the inputs into their country, perhaps. But they would have to remove all of the nodes before they could shut down the blockchain. And then because of cryptography, we can be confident about the validity of the transactions that we see. We can be sure that they haven't been tampered with when they go across the network. Okay, so that's kind of a large overview of what a blockchain consists of and what the important features are. I just want to mention now really the blockchain data structure and go into a little bit more detail to give you an idea of how this really works and how we're able to get this public system, how we can get consensus on that and how we can be sure about the validity of all of the information in that. And why do we call it blockchain? So this is a diagram to give you a generalized view, an idealized view of what blocks look like in our system. And it will start with a block 0 called the genesis block, and then proceed, and over time more and more blocks will be added, and I'll go into the process of that in a second. And in each block there are two important areas. One is the transaction area, so all of the transactions that have happened since the last block will be put together and put into a transaction area in the block. And then the second area, and perhaps the most important one, is the header of the block. Now this will have some information such as the time that the block was created. But the particularly important part is the idea of a pointer in there. And this pointer is effectively a fingerprint of the header in the previous block. Now, we're doing this because we want to be sure that, so as I was saying, the transactions, we get a fingerprint of the transactions and we put that fingerprint in the header of the block. And then we also, in the header of this block, we have a fingerprint of the header from the previous block. And this is done to avoid people being able to effectively forge blocks in our system, or to make it so that if they did try to do that, there would be a really, if you think that we've been producing these blocks, so if you take the case of Bitcoin, we produce one of these blocks every 10 minutes or so. So we're producing these blocks every regular intervals. If at after we've got a few thousand blocks, for example, if someone comes along and tries to say that here is block number 2, and add to your local ledger and to replace maybe the block you already have, you'll be able to check whether that is valid, because you'll be able to look back and check all of these fingerprints in the block, and so you'll be able to see whether that the headers all effectively match up. So if they put some extra data, say, into one of these blocks, then in order for those headers to match up, they would also have to alter the header in the next block, because the fingerprint in the next block would no longer match. And if they did that, they would have to add a new fingerprint into the block after that, and so on. So from the point of view, from a computational point of view, the price of doing this will be extremely high. And in fact, as we shall see in a network like Bitcoin, we rely upon the economic cost of malicious behavior to enforce the security in our network. Okay, so this, as I say, is an idealized idea of a data structure. Different blockchains will do things differently, so this is may not be done the same in many blockchains, but this is a general idea of what a blockchain looks like. And this is why we call it a blockchain, because we have a number of blocks and they're all chained together. Okay, now let's look a little bit more detail of how do we come to consensus. So I've said that we get these blocks being produced every so often, but how does that happen? How do we decide which blocks we should accept? How do we decide who is going to produce a block or which transactions are included? Well, if we look at this from a network point of view, and you imagine that Alice here is going to send a transaction into our blockchain. So perhaps she wants to spend some Bitcoins. So she wants to put a transaction into the blockchain to show that she's going to send some Bitcoins to her friend Bob. And if we also imagine that at the time that she's doing this, the latest block is here represented by the blue block. Now, the idea of a blockchain is that the absolute truth about the blockchain is the state of the system at any one time. And there is no one to appeal to if you decide, or if you think the state should be something different, if you think your balance of Bitcoin is different to what it is showing, that there is no one to appeal to, there is no central authority. The absolute truth about the blockchain is contained within the blocks that we have. So in the current block and in the preceding blocks, and that is the only source of truth. So what we're concerned with when we're updating the consensus is how to achieve this, single source of truth fairly and accurately. Let's go back to our example. Alice here is going to send a transaction into the network. And so she sends in her transaction to a particular node on the network. And because of our gossip network, that node will gossip the transactions around to other nodes like this. And then after a while, it will get picked up and put in a block, and that block will become the current block in our system. And it will have a pointer, it will have a fingerprint of the previous block header within that block. So our latest block is the yellow block. As we go on, more blocks will be produced and our system will get updated. But that gives the idea of how do we come to consensus. So we want one absolute source of truth in our system. We want everybody to agree about the state of our system. But what happens if we have this situation where maybe in one part of the network we have some transactions that are being passed around the network, such as the gray ones in the top left here. And then in another part of our network, maybe we'll have these green transactions. And so now, if you're a participant here, see that there are three possibilities. Maybe you've not seen either transaction, or maybe you've seen only.
I changed something such that your screen isn't sharing anymore. If you want to reshare that.
Okay.
Right, I was trying to stop people sharing their screen. So if you could reshare that, that'd be great.
Yeah. Yeah, you've disabled me from sharing, so you'll have to.
I know why. Okay, yeah, try again now.
There we go.
Sorry.
Okay, so we could have this situation where different people in different parts of the network will have potentially a different view of the state of our system, because some have seen the transactions, some have not come to consensus about this. And how do we decide what the state of our system is at a particular point in time? Well, what we say is that since all of these nodes are effectively equal, and none of the nodes are special, why don't we just pick one node at random, this person, to tell us what the state of the system is at this particular time? So effectively, they will share that point in time, and everybody else in the system will accept that that is the truth about the system at that point in time. So that seems a nice, fair way of deciding this. But obviously, there's an added problem here, because we don't have a central authority. So how do we pick someone at random to give us the state of our system? So what we do is we have a process called mining. And really here I'm talking about blockchains such as Bitcoin and Ethereum. A process called mining, a process deciding who is going to produce a block. And the way we do it in Bitcoin and Ethereum, the proof of work consensus, is that we say, well, in order to pick someone effectively at random and to make this fair, what we'll do is if you want to produce a block, if you're interested in mining, we will give you a puzzle to do. We'll create a race, and the person who effectively wins this race will be allowed to produce a block. And we incentivize people to do this by giving them a reward, or the block reward, if they win this race and produce a block. So all of the people who are interested in creating the next block, in doing the mining, will run special software to enter into this race. And the race that they have, what they're trying to do is to solve a mathematical puzzle. And this puzzle is very difficult to solve. And there is no way to work out how to solve it. It's just what you have to do is make a guess. And effectively, at a number as many times as you can, you do this as frequently as you can, and you put this through a hash function, a special mathematical function, which gives you an output. And if this output is low enough, then you have effectively won the race, and you can send out a block. There is no way of knowing, you make the guesses, whether the number you're guessing will be low enough. So all around the world, all around the Bitcoin network, there are tens of thousands of people making billions of guesses each second as to what a number would be that will produce an output that is low enough. But this is so difficult that on average it takes 10 minutes for one person in the world to actually find a number that will work. So once somebody does find that, what they do is they put their answer, the guess that they made, they put that in the block. And then they also, to get this reward, they put a transaction in the block to pay themselves some tokens, so maybe some Bitcoins. And then they pass that block around the network. And a special these functions that are used in this puzzle is that it takes a long time for us to guess a correct value, but it takes us a very short time to validate that. So all of the other participants in the system who are running their own nodes will be able to take this block and verify very quickly that the answer that the winner produced was a correct answer, and that they did indeed deserve the reward that they got. And once they have that block, then they can use that to then update their local ledger, take the transactions from that block and apply those to their ledger to get the updated state. And because everybody has accepted the same block, there will be agreement across the network about the state of the system. So that was a very, very clever idea that was invented by Otto when Bitcoin came out. A very clever way of consensus in an open system. And with Bitcoin, because the effort of making these guesses is computationally very difficult and requires a lot of electricity, then there is a large economic cost to doing this. And so this also secures our network. So if somebody tried to do this, to provide an alternative view of the blockchain, and they tried to produce their own blocks, they would also have to go through this process of winning this puzzle, and it would cost them a great deal. This is what secures the Bitcoin network, is the economic incentive or disincentive to malicious behavior. We also could have another problem and have two people producing a block at roughly the same time. So you could get the situation here where a block has been produced. The green miner and the red miner blocks fairly quickly, and maybe they don't know about each other, and so they've both produced the block, thinking their block will be the latest one. And so we need a means of decide which of these blocks to follow. And there is a simple heuristic for this, in that we follow what's called the longest chain or the heaviest chain. This is not just the number of blocks involved, it's also the amount, effectively the amount of guesses that were done in producing the blocks. But there always is a way that we can decide between the red and the green block here if we have this situation. And so the next person who comes along will decide that the red block is the one that he should follow. And so this brown block will then have the fingerprint of the red block header in that block And so that chain will then proceed. And so we won't have any disagreements about the state of our system. Everybody will be following effectively the chain that uses the red block. The green block is orphaned. It's not the case that any information is lost, though, because if there were transactions in the green block that are not in the red block, they will probably be picked up in the brown block or in the next blue block. So no information is lost. The only difference really is that the miner who produced the green block will lose his reward. So he won't be happy, but the red miner wins in that case. Okay, so that's the mechanism by which we come to consensus in our system. It's not the only mechanism that can be used, and I've just given a couple of links there to other types of consensus mechanisms. So you'll be hearing from Avalanche and Polkadot later this week. They have consensus mechanisms. If you're interested in seeing how they are to explain those. People have come up with different mechanisms for different reasons. Some of them have been to avoid this economic cost, the cost in energy that is required in Bitcoin, for example. Other ones are trying different mechanisms to increase the scalability of the blockchains. So proof of work is not the only one, although it was really the first one in a realistic blockchain. And it is the one that is currently used by Ethereum, although that is also going to change soon. Okay, quick history where Bitcoin appeared. At the left-hand side, we have really the beginnings of the internet. We got public-private key cryptography and advances that helped lay the foundations for what eventually became blockchains. In the 80s, we had people trying to build something similar, so trying to build electronic cash systems of some sort, but it really was only in 2008, 2009 that we got something feasible. So Bitcoin was invented by Satoshi Nakamoto. Nobody knows who he is. It's not that Satoshi Nakamoto who had to put out a disclaimer. He wasn't Satoshi. And it's been a fantastic system. It's worked very well for a number of years. With the background of the financial crisis, and so in the genesis block of Bitcoin, there's the ability to put data and the headlines to talk about the financial crisis. Okay, so that was the situation in 2008, 2009, and for a couple of years, people are very happy going on with that, and also producing perhaps variants, Bitcoin, similar coins, but vanity coins or coins that had perhaps a different consensus mechanism, but they were doing roughly the same kind of thing. And people tried to extend Bitcoin to do other things. Because of the way it's designed, it is perhaps a little difficult to do that. And its use was really still, main use was really still about transferring value. The next breakthrough came in about 2014 with Ethereum. And this introduced the idea of the idea of smart contracts and the idea of a programmable blockchain. And the idea behind this is that in our blockchain, all the participants have a virtual machine. And this virtual machine is capable of running programs called smart contracts. And the state of them is the state of all of these on the chain, and all these small programs. And so when the way this works is that when Alice wants to create a contract, she writes it locally, submits this to the blockchain as a transaction. This gets passed around in our Bitcoin transaction got passed around until everybody has a copy of our transaction. And then once everybody has a copy, then they can interact with her smart contract and use it. They can call functions on it. The Ethereum simple machine, I won't go into the details about that. We'll do that in another workshop. It's important to know that in smart contract there are some restrictions. One of these is a concept called gas, and this restricts the amount of computation that can be done within a smart contract to stop people doing a denial of service attack on the blockchain. Restriction is determinism, because we're because we want the blockchain the state of the chain to be a all apartment, then we need all of the contracts all of the computation in the contracts to come out with the same result after all of the function calls. So therefore, all of the code has to be completely deterministic and has to be come out with the same results no matter which this is run on. And so for this reason, we do not have, say, floating point arithmetic. We don't have allow random numbers. We also don't allow people to get from within a smart contract to get data from the internet, because that could be problematic. And so we rely upon things called oracles to get data for us if we need data in our contracts. So if you imagine a situation where a smart contract wanted to get some weather data, you could get the situation with different machines on the network that they would get different results, or maybe they wouldn't be able to. For this reason, we rely upon oracles. And an oracle is a trusted third party. It's not part of the particular blockchain, but it's a trusted third party which acts as a means of going to a data source, getting some information for you, and pushing this into your smart contract as a transaction. And because this comes in as a transaction, then everyone upon the network will get can be sure that we will have consensus. Now, if you're writing smart contracts, we can write these in a number of languages. Now, looking here at the Ethereum virtual machine, allow different languages. In Ethereum, the main language is called Solidity. It was a language written specifically for smart contracts on Ethereum. The ones, but Solidity is the most popular one. And in the next workshop, we'll show you how to write that. Let me quickly give you an idea of one of the development that you can use if you want to write a smart contract. So share this screen instead. If you want to try writing a smart contract in Ethereum, the place to start is to use a thing called Remix. This is a development environment that you can run in your browser. You just .ethereum.org, it will bring up this environment for you. It allows you to write contracts. So this is the code that you can see in the main area here in the center. So this is a contract written in Solidity. So on the left-hand side, we have some that you can use. You have a compiler, so you can compile your contract, and then you have a means of submitting your contract to different blockchains. So the typical workflow will be that you will write your contract, say in Solidity, you will compile it, and then you will choose an environment. From here, you can choose different environments. So the one I have here is just a little in-memory, in-browser blockchain that is not connected to anything else, but you can use that for testing. And then you can then click deploy, it will deploy the contract, and then you can test out the various functions. Now, unfortunately, we don't really have time to go through Solidity in much detail here. I can give you some links to a Solidity tutorial, but it's quite a straightforward language. People think that it looks pretty much like JavaScript in syntax. I think it's quite easy to pick up in terms of the syntax. There's very familiar things such as functions. We have variables. So when you have variables, you have to show the type. So here, this variable score is a numeric type. It's an unsigned integer of a certain size. You also can have structures which allow you to put different types of variables together. So it's quite familiar from that point of view. What I think is harder is really understanding and thinking about the decentralized nature of computation and getting used to that, and also the security side of things. Security is very important on the blockchain, and so you really have to have the mindset of assuming that your contract is out in a malicious environment. People will try to take advantage of it or find vulnerabilities in it. Okay, I'll go back to my slides. Okay. as I say, I don't have time this evening to talk about it. There is a tutorial there. You want to learn how to code in Solidity, it takes you through it. So we also have a number of videos as well that will take you through it. And in our next workshop, we can take you through how to write, going from a smart contract and how to gather from that. But one of the things I say, the most difficult things, is thinking about decentralization. If you think, imagine you're trying to write a simple game such as rock, paper, scissors, and you want to write a smart contract to do that. If you do this with traditional technology, it would be quite straightforward. You have central authorities, but in decentralized the Ethereum blockchain and with smart contracts, this is quite difficult. And to illustrate this, imagine you're playing this. Imagine Alice and Bob are playing this, and they are going to submit their moves in this game to a smart contract, which is going to validate their moves and decide upon a winner, and maybe give them some prize for that. Well, if you did this in a very naive way, then you would have Alice submitting her turn, what she wants to play, to the smart contract. So perhaps she would send rock to the smart contract to show that's what she wants to start with. But the problem is that this is a public blockchain. All of the information is public. So Bob will be able to see the transaction that Alice has played. He will be able to read the transaction. He'll be able to read the thing that she played. He will know she played rock. So it's trivial for him to then make a move of paper, knowing that he will then win. And the smart contract would see that he won and give him his prize. So if that's how you write your smart contract, then it would be a very useless game, because whoever went first would always lose the game. We could try to improve this by doing a commit reveal scheme, by a little bit of cryptography. So here we could use a hash function. So when Alice sends in her turn, instead of sending in rock, she makes a commitment to rock by sending in a hash of the text rock. So this will not look like rock from the outside. It will look like a large number, but it is based on the input rock. Bob will see the transaction, but he may not know what it is that Alice has played. So then perhaps he will make an honest move. Perhaps he will try scissors and send in the hash of that. The smart contract will take those two inputs, and then we go to the next stage, the reveal stage, where Alice then sends in plain text what her move was. So then she will send in rock. But now, because they have both committed to their moves, Bob cannot change his move. He's already committed to his move of scissors. So he has to send in his reveal part. So he sends in the reveal of scissors. The smart contract can verify both moves. The smart contract can verify, they take the hash of those two moves and verify that's what was done in the commit stage. And the smart contract can then decide on the winner, which in this case would be Alice. So that is an improvement on the game. It is still not perfect though. There are still lots of problems with that, lots of vulnerabilities. I'll leave that for you to think about. But it's really, this illustration was there to show you just how difficult it can be to do some simple applications such as a game within a smart contract. Because of the public nature of the blockchain, it can make things much more difficult. Okay, if we go to some best practices, now obviously you'll need to read this after you've had a look at Solidity if you don't know that already. The consensus have a list of best practices. I really urge you to read those. There's a link to them there, and they will help you make sure that your contract works properly, make sure that your contract doesn't have vulnerabilities, because if you put your contract onto the mainnet with vulnerabilities, they are to be found and exploited. And huge amounts of money have been lost in smart contracts on the Ethereum mainnet. There are some good patterns also. There's a link here to some useful patterns to follow. One of the best resources you can use is a project called Open Zeppelin. This is a set of libraries that that give you some of the most common functionality that you will need in your contracts. So, for example, there's a contract called Ownable, which allows you to set the owner of a contract, so to give someone specific elevated rights, administrator rights in your contract, or access control. Also allows you to limit who can call your functions. And these really are fundamental ideas that you will need within your contract. Also, if you're going to use tokens in your contract, the basic token contracts have already been written. Please use these if you can. So the ERC20 is the basic standard for a token on Ethereum. This contract has already been written. It's in the Open Zeppelin project, along with variants allowing you to mint it in different ways, to burn tokens, all of the variants they do. So rather than reinventing the wheel, please do use these standard libraries. And they have been audited. They have had lots of people looking at them. You can be sure that they are secure. There are other useful utilities, for example, for mathematics, for introspection. Portable is useful because it's from a security point of view, it's very useful to allow your contract to be paused, to give yourself what's often called an escape hatch, because once you've deployed your contract on the mainnet, you cannot change it. It's I often think it's a bit like putting software into a spacecraft. Once it's been launched, it's out there, and it's very difficult to fix any problems that you have. But if you make your contract pausable, it will mean that you can stop people interacting with your contract if there is a problem, and it'll give you time to look at the situation and then see how you can solve it before too much damage is done. We'll have another workshop where we can go through how to write a decentralized application if you already have a smart contract. And this is done using called Web3 libraries. The most popular ones are written in JavaScript, so they are the Web3 JS libraries, and the means to interact with your contract from some external source, such as a web page or an app on your phone. If you don't want to use JavaScript, there are also plenty of other alternatives. There are examples in Java, in Rust, .NET, PHP, lots of different languages. So whatever language you're comfortable developing in, there will probably be some libraries to help you interact with your smart contract. If you've got to grips with writing a smart contract and deploying it, a good thing to use next, another very useful development tool, is Truffle. This is a suite of tools that will help you in your development. It's a command line, so in some ways I think Remix is easier to use initially, but it allows you to write unit tests. It also has lots of boilerplate code around the Web3 libraries, so allowing you to build up DApps very quickly. So I really would recommend that as well, and using that once you've got a little bit of familiarity with writing smart contracts, so you can then use something like Truffle to stay and to increase your productivity that way. Now, if you I went through this far, but we have plenty of resources to help you. As I said, we're very keen on community education. We try to do workshops as much as we can to spread knowledge about blockchains. If you go to our education site, there are lots of videos on there and tutorials about writing smart contracts. We also have information about zero-knowledge proofs, because we do workshops about those as well. I think I know Beam are coming later in the week, so you may need a good background on zero-knowledge proofs if you're going to look at their challenge. We have more detail about security, some DeFi, and if you want to play a game, we have a capture the flag game. So this is a number of levels that you can play that are all around writing secure contracts, finding vulnerabilities in contracts. So it's just a simple game. It's on Rinkeby network, so you can do it without cost. You're not paying for transaction fees. So yeah, please feel free to have a go at that game and test out your validity and your knowledge of security. Okay, I've rushed through that to give us at the end for Q. These slides, you can get them at this. I'll just take the screen and okay, quickly. If you have questions.
Awesome, Lawrence. Thank you very, very much for that.
Okay.
Should we deal with some of the questions?
Sure. Yeah.
Let me see if I'm gonna, guys. So please put your questions into chat, and we'll see if we can handle these. So I'm looking. How does if you want to look through them, Lawrence, I'm trying to see which are questions and which people seem to be asking them themselves.
Okay. Okay, so someone's asking about memory problem due to too many blocks. Yes, so this is definitely a potential problem. So, and it's been solved in different ways. So if you start to play Node, say in Ethereum Node, if you download all of the transactions on Ethereum, all of the blocks, it requires about I think about 4 terabytes now. It's a huge amount of data that has gone into Ethereum. And so for this reason, there are different types of nodes that you can run. So some nodes maybe only take in the headers so they can verify the validity of blocks, and then they will only store a certain number of blocks, and they will build up. They will store enough blocks so they can have a valid current state, and they will be able to go off to what are called archive nodes to get more state if they need it, but they will only store a limited subset themselves. But yes, this is certainly a problem. I did a talk, and hopefully there'll be a video about this available last week by a company called Mina, who solved this by using recursive zero-knowledge proofs, which I think is a very interesting way of solving it. So the question, what is a block? Please, it's not a dumb question. That is what we're meant to answer. Yeah, the block is two areas. One is a set of transactions that have been picked up by the miner of that block that are going to go in to change the state from our last block to our next block. And then we have some header information that allows us to really do the fingerprinting to form this chain amongst the blocks. It has some other information as well, but it's really forming this chain amongst the blocks that is important. Yeah, I think they've been answered. Oh, so how do they don't lie in plain text? So you're asking about the commit reveal thing. Yeah, so in the commit reveal scheme where they were taking the hash, when they revealed their move, if they put in something different, then the smart contract would know that didn't match up to the move that they made initially, and it could detect their cheating and reject their move. Yeah. Oh, sorry. Yes, you've answered that yourself. Great. Okay. Yes, so a very good point from Tamir. Yes, that's exactly right. Bob could create hashes of all the possibilities and then work out from that what it was that Alice played. So that's why that is, as a first attempt, it solves some of the problems, but it doesn't solve it completely. But that's good that it's good you're thinking of this. See, this is the process you have to go through when you're trying to solve this or to write applications on a blockchain. You really have to think through the fact that people could try to cheat and how you're going to get people to be honest. Yeah. So how are smart contracts added to the chain? So they're added just as a simple transaction. So you write your smart contract in a higher level language, such as Solidity. That is compiled into something called bytecode. So it's a more compact version of that contract. That is submitted as a transaction to the blockchain. So that gets passed around and stored by everyone. And then in terms of execution, yes, it's a very important point, and I'm sorry I missed this. the important point is that the transactions, which are actually function calls in the contracts, they are executed by everyone in the network. So it's not the case that the work is distributed in the network and the people do different things. It's duplicated. So every virtual machine on the network does the same computation. They run the same functions with the same input, and they will get the same output. And so they will use that output to update their local state. And then that local state should be the same as everyone else's local state. In terms of how that happens in time, and when you say do miners execute them, yes, they do. So the process is a little more long-winded than that. So it starts with Alice submitting her smart contract, and that is distributed. Everybody gets their copy. And then when Bob wants to call one of the functions in that, he submits a transaction saying he wants to call a function and saying any parameters he has for that function. That transaction is passed around, is gossiped around the blockchain, and eventually it will get mined. And so the miner will then have this set of transactions, this set of function calls that are going to be run in all of the contracts. So the miner will then be able to run those transactions against the contracts that he has locally. He will then do that. He can validate that these transactions make sense, as can anyone else. He will then bundle these transactions together, put them into a block. He will solve the proof of work puzzle, and if he wins, he will send that block out, and then everyone in the network will receive that block. And it is at that point, once they've received the block, that they will then go through and run the transactions in the order that the miner specified them. So it's important to understand that when the transactions are run in your smart contract, they will be done in the order that the miner has included them in the block. And it's possible that the miner may have dropped your transaction from the block. He could decide not to include it, and it could be picked up in a later block. So there's a couple of assumptions that you shouldn't make about your smart contract. You don't know the order of transactions necessarily, and you don't know whether your transaction will be included in any particular block. And yes, it could indeed front run as well. And there's some very interesting articles about this at the moment and the impact of this on DeFi. If you Google dark forest and DeFi, you'll get some very interesting things. It's something you have to be very careful of if you're doing particularly in DeFi, where there's economic incentives to doing transactions. The miners can indeed front run you and drop your transaction and for themselves that does the same thing. Yeah, it's something that you need to think about. What happens if we apply blockchain to all the tasks? Isn't it too scary? I wouldn't say I'm scared. I see what you mean, but I think it's exciting, I guess. Obviously, the blockchain is not applicable to everything, and it does have some drawbacks. Too power consuming. Yes, Bitcoin does consume a lot of power, but in its defense, a lot of that power may be surplus power. It's often the case that the big Bitcoin factories, the big mining factories, are situated near hydroelectric plants and often use energy that would otherwise go to waste. But yes, it does have a big impact in terms of energy consumption, and that's why people have tried doing different consensus mechanisms. The randomness, yes, randomness is very difficult in smart contracts because you want to be sure that everyone who runs your contract gets the same result. There are ways around this. There is a contract called the Rand DAO, which attempts to solve that. You can also try to solve it with oracles as well. Just using kind of a random number library as you would in maybe JavaScript will not work. So you have to be careful. It does make writing gambling applications more difficult. Yeah. I'm certainly happy to answer more questions if you have them, or you can email me them later if you have any more.
Yeah. Any more coming in? Oh, Kirill's going for one.
Yeah. Right. So creating a custom blockchain. Yeah. So a lot of the work I've done with enterprises has been on private blockchains, where maybe they're not quite ready to open up their application to a public blockchain. It's often the case that you will get consortia who, a few companies get together, they run a blockchain between them, they want to share maybe some functionality or have the ability to interact with each other very quickly and in a very safe, secure manner. But and maybe they have some trust in each other, but not completely. So they would like the blockchain to add a little bit more trust in there. And then the incentive is that they can do this. It's more efficient for them to do this. So one example is banks who use this for trade settlement, where previous to this, they would have maybe a clearinghouse. They would do this. It would take perhaps up to 3 days to do this, and it would be quite expensive. Whereas if banks set up their own blockchain to settle trades, they can all agree on the means that the trades are settled and agree on the protocol. They can do this between them. If they do it on a blockchain, this trades settle within a few seconds, and they're not paying an intermediary such as a clearinghouse to do this, so they save a lot of money. So yeah, custom blockchains are often done to save money, to reduce costs in companies. I think it was an interesting comment from Vitalik Buterin, the inventor of Ethereum, who pointed this out, but then said that it's really public blockchains that will produce the exciting applications that will really change society. I think that's very true. I think private blockchains will save you money, may be good for enterprises, may make them more efficient, but public blockchains will bring you the fascinating, really groundbreaking applications that could change society and really revolutionize how we interact. So in terms of the incentive for mining, yeah, so if you're mining and you obviously you're paying for the electricity you use because you're in this race and you're trying to solve the puzzle. If you manage to do it, then you get a mining reward, and that reward changes slowly over time. At the moment, in Bitcoin, it is 6.25 Bitcoins if you produce a block. So it's many tens of thousands of dollars that you will get for producing a block, and obviously that will be more than the cost of the energy if that's going to be profitable. In a gambling application, well, any application still would rely on the same underlying network. So the miners will be mining and get the same rewards no matter what the application that is running on top. So so if you're running a gambling application, maybe you will, the person who wrote the application may ask for the people who are playing the application to give them some tokens. And so they will get tokens as the developer or the company that owns that application. The miners themselves don't get a reward exactly from that, but they get the block reward. They also get transaction fees. So they will get rewarded no matter what the type of application, but that comes in the form of the mining reward and transaction fees. Yeah, so I hope that answers your question, Patrick.
Awesome. I think any last questions? Sweet. Well, I think my microphone is definitely playing up. My mic. Can anyone tell me if my microphone's good or bad?
Sounds fine to me.
Okay, I'm getting this weird kind of back noise. Anyway, probably just me. Lawrence, first of all, thank you so much for another great talk. I know all of the individuals found it very enjoyable and very educational. And yeah, thank you so much for your time, most importantly. We are hopeful that we'll have another one schedule allowing next week. So do join us for that. Lawrence, what would the topic be? It would be smart contract stuff, right? Oh, Lawrence, you there? You've muted yourself. I have to now allow you to unmute yourself.
Okay. Yes, it will be given a quick issue of solidity, and then how to take a smart contract and create a decentralized application from that.
Awesome. So that sounds very fun and very useful for those building their first applications. So thank you again, Lawrence, and do check out Extropy.io. Some unbelievable educational resources. They put on a ton of workshops and in general are excellent with all things to do with blockchain development, both educationally and obviously for if you're looking to engage their services with help for a professional project. One thing I want to say, guys, is I'm very sorry if anyone was disturbed by what was shared by that one person. Obviously, we kicked them out as soon as we could, and it was quite. I didn't see it myself, but I've been told it was quite disturbing material that was shared. So we're very sorry that happened, and we will be doing everything we can to A, find that person, B, make sure they don't join any of our events, and C, just put in place a few practices to make sure that if anyone does try and troll or share disturbing material, we can crack down on it much faster. So we're very sorry for that. Again, thank you very much, Lawrence. Thank you, everyone. We 3 more events this week: Tuesday, Avalanche Workshop; Wednesday, the kind of Welcome To, where if you miss Welcome 1, I come to Welcome 2, and also if you attend Welcome 1, come to Speak Finance to introduce their challenges, Raiden and Beam doing so too. And on Thursday, we have a Polkadot event as well, and then a whole nother series of events next week. So do follow the Discord, follow the Medium, follow these slides, and this video will go up on YouTube, and again, follow the Discord for everything. But for all now, guys, thank you very much. Have a wonderful evening, afternoon, mornings, wherever you are. And Lawrence, thank you very much again.
Thank you.
Thanks, everyone.